Thank you so much for having me here. I really appreciate that. So I joined Two Sigma a couple of months back. But I'm not really going to talk about what I do at Two Sigma. I will talk more about what I do as hobbies, that I do as research, and also what I did in my previous job. The one topic that has been fascinating to me, and that's partially also the biggest challenge I'm kind of really excited about in finance, is this notion of predictability. How predictable are things? I mean, if you go back into the history of humankind, and by the way, I'm not making any investment advice here, just like, let's get this out of the way. People have always been fascinated with predicting stuff. There were oracles of Delphi that people ventured to, or prophets that knew what would happen. So it has always been a real kind of strong interest of humankind. And for the most part, that's the same thing we're now looking for in finance and in many, many other application domains. What I'm really interested in is how that plays out when it interacts with different machine learning algorithms, and sometimes how it can actually hurt you in very surprising ways. So what do I mean? I've worked on very different tasks, from something in genetic applications to consumers to marketing to now finance. And there is this vast spectrum how well you can possibly do. And the funny part is you never know how well you will do. You can work on the same problem for another 3 weeks, and maybe you get 1% better, or maybe you don't. It's just kind of this vexing issue in machine learning. But you know there's an ultimate limit to how far you can get. And so on this spectrum, it has nothing really to do with the algorithm. We know you won't do very well in the stock market. If you get accuracy of 60%, you are not sitting here. You're rich somewhere, right? It's like, there's a fundamental reason that we can't predict very well, and it will never go away no matter how sophisticated the technology will get. On the other end, is this a cat? That's the space where deep learning now just kind of owns everything. That space where we have gotten really, really good, but realistically, any 3-year-old is very good at that. In fact, much better than any financial analyst is at this. So there is a limit to how well you can do. And it's also true to a lot of the applications I used to work on around human behavior. How predictable are we? Well, sometimes we're surprisingly predictable, and sometimes we're not. So there was the Facebook study that showed, based on very little information, it's very easy to predict things, for instance, like sexual orientation. Am I going to have pizza tonight? I have no idea. I don't know when I'm going to get to the airport and whether the flight is delayed and how hungry I'm going to be. I don't know whether I will have pizza tonight. Good luck to any algorithm trying to predict that. So again, you have the spectrum. Things are hard to predict and some things are easy. I want to really focus on a particular example to showcase what happens in machine learning algorithms depending on this. So we'll pick a simple task here. We'll just predict who is male on a data set that Facebook published a long time ago, where you basically have these IDs for about 200,000 of their users. It's all anonymized, but you do have a flag, people self-declaring their gender, and they were 40% men. You also have the things they liked. So you have, again, anonymized IDs pointing to certain objects here, and for about 100,000 of different objects. So we're going simple, but I don't think what I'm trying to demonstrate really depends on the complexity of the algorithm. All right, shall we? Let's try to predict gender purely based on age. How well do you think I'm going to do? Well, it's on that side of the world. It's the very difficult part. It's not quite 50% because, remember, there were only 40% men, so you had to get at least an accuracy of 60%. But that doesn't really matter. What's not interesting here, let's look at what, for instance, the AUC says. So the AUC is a measure between 0.5 for random and 1 for deterministic. Slightly better than the stock market. Not by much. 0.58 is not great. What I really want you to take a look at is the distribution of the predicted probabilities on the test set. And what you see here, they nicely center around 0.4, kind of normalish distributed. Now, if you use a model like this, what typically these models are used is to identify people who are most likely to do something. Or if you want to target males, then you only pick the ones where the model has the highest prediction. So let's look at the top 1% highest predicted people. Turns out you're not that terrible there. 75% of them are in fact male. Okay. Shall we actually add some larger data to this and add in particular the likes to the feature sets? I'm not adding more training examples, I'm adding more information. What happens, do you think, if I give it all of your likes? Accuracy is actually not that great, 83%, but look at this. Now that's a very opinionated model. That's a model that it knows something. So you see how the predicted probabilities have kind of migrated all the way to the extremes. For many people, the model is pretty sure it's either 0 or 1, either male or female. No more doubtful, well, almost. Now, of course, over here, you get 100% correct, so all is good. What's going on here? Who are these people where the model still can't make up its mind? Nobody wants to guess? So it's quite interesting to see, depending on the audience, what people kind of stories come up. Nope. There's actually no deep meaning to this whatsoever. That's people without likes. This is no data. We're back to where we started with age only. Okay, if you actually play this through and look at the progression. So initially, that's where we started, just age. Now I'm adding the 10 most commonly liked things, not even the most predictive, just the most common liked things. All right, it starts to spread. And then as you add 100 different things they can like, so 100 dimensions, 1,000, 10,000, and this is the full 100,000 kind of sparse representation. You can really see how the model behavior changes in terms of the distribution. All right. Now, where am I going with this? Because very often in the real world, when you build models, it's not one or the other. There are parts of your population that are predictable, and then there are other parts that are not. So you're having these mixtures sitting. And then, if you just let the model go where it wants, it will focus on what's easy. And it will ignore the hard part. Let me tell you a story from my advertising days. So we were building models to target people. And over a very short period of only 2 weeks, the median performance over hundreds of models in terms of lift doubled. Now, usually that's great, I guess, except that I hadn't really done anything. And if models in machine learning look too good to be true, chances are they are too good to be true. So we started investigating this particular case, because I have a hard time believing that people are getting more predictable. Now I have to come clean what the actual data looked like for that, so let me talk a little bit about this. So this is a distillery who collects basically browsing behaviors, histories, and then we work for marketers like, for instance, Microsoft Azure. So if we need to run a campaign to identify who might be interested in Azure, we basically build a model that predicts this particular outcome, why we have seen a person going to Azure, based on all the other things that the person did. So it's like a classical targeting operation where you build very large-scale, high-dimensional models that predict very specific outcomes for a given marketer. So for instance, this is a model here. It's a logistic regression. Right now it has about 360,000 non-zero parameters, and it's built with gradient descent and all the kind of usual bells and whistles. If you want to know more, I'm happy to share the paper that was published on that. But it just gives you a flavor of what these models are, and then you see also the coefficients here. And not very surprising, you have things like Microsoft Blog and Office and other software things showing up as being very indicative. All right, so just to give you a flavor of what these models are that all of a sudden perform very well, when we started looking inside them, we found really surprising stuff. For instance, people who go to women's health base are much more likely to show interest in luxury cars, Microsoft Office software, credit cards, pizza, and hotels. And it wasn't just women's health base, there were other very predictive sites showing up that nobody really had ever seen before. So let's look into this. And I'm going to share what we call an overlap analysis, where we look how many of people who go to one website also go to the other. So it's kind of an overlap. And I will draw a line between two host names if more than 50% of the cookies or people we saw on one also shows up on the other. And I know that because we get about 100 billion bid requests in the exchanges from programmatic advertising. Again, if you want to know more about that, I'm very happy to take that offline as well. It's a wild west out there in that space. So this is what the graph of this is kind of the host name graph looks like. To give you a sense, let's take a look at some of these smaller structures here. These are all sites around Boston. The Boston Herald and Search, and for technical integration and other reasons, it probably makes sense that you see this kind of traversal of cookies that go from one to the other. Now, what about that thing? Well, this is where our friend Women's Health Base is, right there. And I would like to point out just the sheer amount of time these cookies spend on the web, and also the very diverse set of interests. Wrestling news and China on TV and others. Now, there's no way that this is a person. I can't imagine a single person who does that, let alone a whole bunch of them. What you see here is basically the digital fingerprint of a bot network. All of this traffic is not human. These are all bots whose sole purpose is to fraud the advertising industry. It's a beautiful business model. So what happened here is there was a transition in kind of the strategy of advertising fraud, from the naive fraud to the more sophisticated one. Because so far I haven't explained really how predicting Microsoft Azure is all of a sudden getting easier. Well, it turns out you have exactly the scenario of two different populations. You have people like me who are not terribly predictable, and then you have bots. And around the time, the percentage was around 36%. The clue here was that bots started not just visiting these weird websites, but also legitimate ones. They went to Microsoft Azure and to Chase.com and to Nike and Guthy-Renker. This is called cookie stuffing because it makes the bot much more interesting for the advertiser because they have showed intent. So now the bid price in the auctions go up, so you can monetize these bots a lot better. And so the owner of the bot realized that making them do what advertiser measure is a way to make them more valuable. And now all of a sudden, this is exactly what I'm trying to predict, going to these websites. And this is where all of a sudden it became a lot more informative and the signal showed up. To give you a sense of how widespread this is, the most extreme case is the video completion of the Clorox campaign. And yeah, not surprising that only bots are patient enough to sit through all of these Clorox videos. So on the spectrum, we have exactly this case where people are kind of predictable, but bots are either deterministically written to do it or not. They're very predictable. So what happens then is you get this mixture in the distribution where my model very quickly realizes, oh, here's an easy one. And if you now try to target, guess what? Out there, you end up only reaching bots because the probability scores for people never get large enough because they just aren't deterministic enough. There's not enough signal. Once we build a bot identification software and got rid of that signal, then my performance went to hell, and that was a good thing for once. So what about clicks? Okay, who here recently clicked on an ad? Okay, let me rephrase. Who recently had something popping up on their computer and realized they must have accidentally clicked on an ad? Good. So you have the same problem with clicks. It's not strictly speaking true that every click is an expression of consumer intent. It may occasionally be, but not always. A good chunk of clicks are accidental. And so, for instance, if you look at the models that predict click-through rate, the highest predictions are, again, the accidental ones that are easy to predict. And I'll tell you why they are easy to predict relative to the intentional ones. Intentional ones are still difficult, but accidental ones, what you think is random, is not random. Your accidents aren't at random. Your accidents happen, for instance, on this one, because, gee, you can't even find the place to switch it off. It's the little, almost the same color as background gray here under the. So another symptom, by the way, is you just need to show the ad on the flashlight app. That's when people are fumbling in the dark. Doesn't mean that you're interested. It just means there's a high chance that you are distracted. So that poses an interesting problem. In the old days, we still had a lot of accidental clicks. But as long as the intentional click rate was higher, you could somewhat correctly distinguish in saying, well, maybe if the click-through rate is higher for my population of males here, I should be targeting males. So the accidents in the old days when you didn't have information didn't hurt you. But once you can target, and this is this example of the flashlight app, you see that what used to be random becomes predictable, which has a lot of information. And there are specific games that always have very high click-through rate, and so have flashlight apps. So these are kind of the highest ranked parameters in the model here. So okay, basically, website stuff is fraud, clicks are accidents, what else can we do? Well, how about we try to predict whether people actually go to the store and buy the thing I'm trying to sell them. So let's build a model that predicts who shows up at the car dealership in person. No bots, like real people. Now I have to come clean about my data. So I have a lot more data about, well, Distillery has a lot more data about you than you may believe. It's not just your web browsing, it's also all the stuff you do on your mobile phone, including where you go, unless you're very diligent about switching off your GPS all the time. And chances are I can connect these devices based on IP addresses. That lets me identify your home IP based on some heuristics. So if you look at this, you basically can tell on occasion whether a device is at the car dealership. Because what do you do most of the time at the car dealership? You're sitting around and waiting. And then you pull out your phone and you play Candy Crush 15. Chances are it was for free because it's ad monetized, which means it tells me where you are. So I know this part. The lat-long information is not necessarily very reliable because of granularity and various other things. I'm also a little bit uncertain about associating your phone to your browsing history on your desktop because it could be your significant other or other people who are in the same location. So there is some uncertainty about this. But basically what I will do, I will predict who goes here based on what they did online before. Are we clear? So this is the predictive task I'm posing here. OK, now, if you think about what's going to happen, you really have 3 different scenarios. You have people who indeed went to the car dealership and their browsing history. Then you have people who may have looked like they were at the car dealership, but actually just sat in the coffee store around the corner. And then you have people who may or may not have been at the car dealership, but it's really the neighbor who hacked into your Wi-Fi, which I have as your features. All these kind of scenarios can play out here. Now, what's going to happen when we build the model? Here's the model. Here are the highest kind of top 30 websites that are most indicative of a person showing up at a car dealership. Let's look at this. It's actually very interesting. You have a lot of in-the-market signal, like people doing research about cars. I always thought this was kind of a myth, but it turns out that there is clearly a correlation between real estate activity. So people do buy cars after or while buying houses. And then you can make up your own mind why there's kind of upscale fitness going on here for BMW, but I'll leave that to you. So what's the verdict here? It actually seems to be a reasonably good model. I mean, what I'm seeing here is that the model indeed found people who were interested in cars, for the most part. And all of the other problems kind of went away. That poses an interesting question. How much noise can you have in your labels before models fall apart? And now I'm saying noise in the term of random. So let's play the game and try to figure out and simulate what happens with these three different kind of populations here by mimicking the same thing in our data set on gender. We're going to use this data set, and now I'm going to start changing labels at random. How much can I get away with until this thing keels over? Turns out surprisingly much. So I basically just randomly reassign a label. And what you see here that, for instance, with 50% of randomly reassigned labels, so 25 are correct and 25 are randomly wrong now, you still have, this is the wrong one, you still see at 50% more than 97% correct in the top 1% predicted, which is very surprising to me, or was initially. So what happens here is that while the distribution gets sucked in again a little bit, it keeps the kind of spikes on the outside. The signal prevails because everything else is going, is just random noise. So what that means here really, the people who really wanted a car, this is where the signal was. And the people who were just in the coffee shop across the street or who had hacked into your Wi-Fi, that was random noise that the model couldn't explain. And therefore, it almost works like a low-pass filter, where you're left with only the good stuff. So for once, we actually got lucky here in this case, that it was exactly what we were hoping for. OK, let's move on to the last very interesting group of audience for advertising, frequent travelers. Marketers love frequent travelers. A, they probably have a good income. B, bad conscience because they're away from home so much that they buy gifts for the family. So people love to advertise to frequent travelers. Now, where do you find frequent travelers? Airport. Glad that the leading picture always works. So let's actually build a model that predicts who will go to JFK. It worked well last time with the car dealership. Let's see what we get here. Here's my model. OK, let's take a look at this. Whoa. These are kind of religious content sites in Spanish. Now that's interesting. Jump seat news and Association of Flight Attendants. NFL fans. So what's going on here? All the frequent travelers, NFL fans? Well, turns out it's really easy to predict who works at an airport. You don't just have frequent travelers at airports, you also have people who work there. And so the frequent travelers remains elusive and unpredictable, whereas what you really get a good handle of is probably all the people who are working there day in and day out. So on this one, didn't work that well. Now, let's leave the funny stories behind and focus on the bigger picture here. If you listen carefully to what I said, I'm basically saying that the initial distribution, even if it is balanced and fair, can be disturbed by how much signal there is in subpopulation. And if some subpopulations are easier to predict than others, they will dominate the highest kind of scale where everybody is targeting and is reaching out to for various applications. Think about LinkedIn jobs. I'm pretty sure LinkedIn is using a model that predicts success or interest based on resumes. And you can assume that even if you balance initially the pool of coders into equally many successful male and female, there's no reason to believe that this ratio continues into the highest prediction, because the predictability can generate these distortions that we saw before. And we are looking at many of these cases where we're using them for populations that have very diverse kind of amount of information. Some of them you know very little about. they will never get extreme probabilities and extreme predictions. Some you know a lot more about, they were more likely to end up on the extremes. A really interesting case that I would love to understand, because there was a long debate whether this was malicious or a kind of artifact of an algorithm, is what happened in a study that Latanya Sweeney did. She's a tenured professor at Harvard, and she observed that when she Googles herself, she got a lot of really weird ads from companies like mugshots.com, or whether she was arrested before. And then she did a study on this where she showed that when you were searching for names with more racially black kind of background, you were much more likely to be shown one of these offensive ads than if you were searching for John Smith. And it's an interesting question whether somebody targeted racially, whether it's an artifact of certain behavior of who clicks on ads, whether it's just more predictable. It's one of these biases introduced by the model. The bigger story is here. We can't just say, oh, you have to debias your training data. Yes, you have to debias your training data, but that does not absolve us from the responsibility of looking at the prediction and seeing how they behave, because they may very well be biased again in some ways. And if you care about justice in your predictions, you probably have to take explicit steps to, in the LinkedIn examples, give me equally many female and male candidates for this job, no matter what their relative ranking to each other. Thank you very much.
So when we're at the airport, basically we're just noise.
Yes.
It doesn't seem like that when I'm there. I mean, you know, in terms of the crowds that are there. So is there a way then to, so when I see noise, I'm a signal processor, I like to figure out how to filter out noise. How can you use this to filter and then maybe get underneath the data? Is there strategies from that?
Wait, you asked me now how to make sure that you will be targeted next time you're at the airport?
No, I'm not saying that, but maybe there's a problem where you want to do that, where you actually want to find out about it. So I'm just curious about, you know, can you do that statistically?
So can I do something about it? Yes, but one of the reasons, the problem with advertising is that if I'm going to be measured on the click-through rate, what am I going to do? I'll target the flashlight app. Because if I don't, I'm off the program. They will hire somebody else to target people with the highest click-through rate. So the problem is really that the metrics are soft, that the metrics are not really what you're looking for. They're not related to an actual purchase. And that's why you have these distortions. So to your questions, we thought very deeply. I think it hurt us that we built a fraud detection module. It actually decreased our performance significantly.
Interesting.
As a frequent traveler, I don't want to be targeted, but what about things like in your browsing history to differentiate people who work there versus travelers? Like, did you sign on to the free public Wi-Fi that's there? Is that as your browsing history versus those who work there who have access to the corporate?
Let's make it clear. I'm using these examples that were actually all real. These were all models we built. But I wasn't trying to make the problem go away. But I personally like them as illustrations for what happens if you have mixtures of populations. Again, in advertising, that's probably the least concerning case of this happening, and you can just happily close your eyes and go with whatever the algorithm finds, and you are probably better off if you want to run a campaign and be paid again. But I do believe that the symptoms of what I'm showing here are overall concerning if you want to use predictive models and then pick the top N in many other domains where you have to think much more carefully whether you're really getting the right subpopulation and whether that's fair. So it's more of an illustration point than me trying to really find frequent travelers.
Okay. Thank you. Let's thank Claudia again. And judging from that, I think we just all need to unsubscribe and leave the phones at home.